Alright, so here's going to be page 2. Um, Question 6 is still having to do with the mean value theorem. Um, so where we picked off from questions 3, 4, and 5. Um, so it took 29 seconds for the temperature to rise from 9 degrees Fahrenheit to 146 degrees Fahrenheit when when a thermometer was taken from a freezer and placed into boiling water. Although we do not have detailed knowledge about the rate of the temperature increase, we can know for certain at some point the temperature was increasing at a rate of 137 degrees Fahrenheit for 29 seconds. Explain. So, it's just by the mean value theorem. So, 137, excuse me, 137 degrees Fahrenheit is the difference in time. So from when it reached 146 to where it started at 9 degrees Fahrenheit, and 29 seconds was the interval for which it happened. So this is the average rate at which the temperature increased for the 29 seconds for every second. This is the average rate, and so that means that at some point in the time interval of 29 seconds, um, we can know for certain that it had to match that, and so that's just by the mean value theorem. At some point, the instantaneous rate of change was equivalent to the average rate of change. So, um, yeah. Um, Going down to 7. Um, so here we're going to sketch a graph of a single function that has these properties. It's continuous and differentiable, and then it's going to talk about increasing and decreasing. It's going to talk about concavity, some inflection points, I think, or this is the inflection points, and then this is right here. These are the critical points. Um, so f of x is greater than 0. That means the function is increasing. It means the function is going upwards, and it's going upwards on the interval from -3 to 1. So it's going to be like -3 to -1. So it has to be increasing in that interval, and then from 2 to infinity also has to be increasing. So I'm just gonna. This is how I like to do it. I like to split it up in this kind of way. So it has to be. Oh wait, no, that's not increasing here. So increasing here, and then increasing here, which means part C is saying that it has to be decreasing elsewhere. So decreasing and decreasing, meaning it's going down. For these points right here, let me use a different color, maybe green. So I'm going to split it up into some intervals. So f double prime is greater than 0. That means concave up from -infinity to -2. So right there to there. And then from 1 to infinity. So it's concave up. We'll just say C up. Concave up, which means for part, part E, concave down, f double prime is less than 0 from -2 to 1. So concave down. Concave down meaning bowl shape down, concave up meaning bowl shape up. Something like that. It's very unofficial, not really formal talk or definition. So, let's see. Um, these right here are referring to critical points because it's saying f prime at -3 right here, and at -1, so right here, and at 2, so right here, has to have, the derivative has to be equal to 0, and that follows. It just means that there's horizontal tangents. Well, again, that's going to happen just because if we're going from decreasing to increasing, we have a critical point here. So there you go. And then we'll have a critical point here, or sorry, where was that? Anyways, yeah. So these are just referring to the critical points, which will happen whenever you change from decreasing to increasing, or increasing to decreasing, and so on and so forth. And then these are points of inflection. It's saying f double prime is equal to 0 at -2, 0. So these are actually going to be points on the graph. So we'll do -2, 0. The graph has to pass right there, and at 1, 1, so maybe like right here. So these are actually going to be points on the graph right here and right here. And that follows because if we're changing from concave up to concave down, or concave down to concave up, then we have to have an inflection point. So concave up, so let's go ahead and draw what we think this graph will look like. Has to be decreasing, then has to be increasing, and it has to have an inflection point right here. So this is where it's going to have to change from concave up to concave down. Still increasing, going to change to decreasing, and then it's going to have to come down, and it's going to have to change concavity right here, and then but it's still decreasing, and then it's going to have to change to increasing. So your graph might look something like that. So there you go. Alright, here use the first derivative test to determine the local extrema of the function and identify any absolute extrema. So we already used the first derivative test over here, so we're just going to take the first derivative and set it equal to 0. So f prime of x, we're going to use the product rule, so it's going to be the first times the derivative of the second, which is going to be 1 over 2 square root 25 minus x squared. Of course, you have to multiply the numerator by the derivative of the inside, which would be negative 2x, plus the derivative of the first, which would be 1, times by the second, which would be the square root of 25 minus x squared. Okay, and then if we simplify this right here, 2's would cancel. We get negative x squared divided by the square root of 25 minus x squared plus the square root of 25 minus x squared over 1. And before I set equals 0, I'm just going to get a common denominator. So times by the square root of 25 minus x squared times by the square root of 25 minus x squared. That's going to be equal to, so we still have the negative x squared. This right here will be plus 25 minus x squared over our common denominator of 25 minus square root of 25 minus x squared. That's going to be negative 2x squared plus 25 over the square root of 25 minus x squared. Okay, and we set that equal to 0. Thing about the denominator, why we're not going to really worry about that, is because it will be equal to 0 when it's positive or negative 5. And that's going to be the endpoints here, so it's not going to matter too much. And then here, so we'll set the numerator equal to 0. I'm going to do that up here since I'm running out of room. So negative 2x squared plus 25. Set equal to 0. We'll get 25 equal to 2x squared. Divide by 2, take the square root. So we'll get x is equal to plus or minus the square root of 25 divided by 2. So these are critical points. So we'll use that for our first derivative test. So we have negative square root of 25 divided by 2. That we're going to have square root of 25 divided by 2. And we're going to plug the first derivative. We're going to plug values into the first derivative. So let's do f of 0. So if I plug in 0 into the derivative, oops. So here's the derivative. I plug in 0 right here. That's going to cancel if I plug in 0 right there. So we're going to get a positive divided by positive. So here the function will be positive. It means it's increasing. And then we're going to check somewhere to the right. I can't go past 5, so maybe we do f of 4 or something like that. So if I plug in 4, and I know so this, because square root of 25 is 5, and 5 divided by the square root of 2, yeah, 4 should be good. So if I plug in 4 here, that becomes 16, that becomes negative 32, so that's going to be negative on top, positive on the bottom. Yeah, so that's going to be negative, and it will still be negative over here, because if I plug in negative 4, f prime of negative 4, sorry, one second, this is all prime. So if I plug it in negative 4, that's going to give me the same result, so negative, negative. So function is decreasing, then increasing, then decreasing. So minimum here, maximum here, and then I need to plug in these two values into the function to find out specifically what those values are. Yeah. So you just plug them in to get those values. So there you go. Yeah, use the concavity test to find the intervals where the graph is concave up. Concavity test, I need to use the second derivative. So y prime, well, this is equal to 8x to the negative 1. So the first derivative would be negative 8x to the negative 2. And then y double prime will be equal to 16x to the negative 3, which is 16 over x cubed. Okay. And then I'm going to set that equal to 0. So again, concavity test, concavity depends on the second derivative. So if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. And so obviously if the second derivative is going to if it's going to change from positive to negative, it's going to be 0 at some point or something like that, or undefined. So in this case, if I set the second derivative equals 0, well, the numerator is 16, which can never equal 0. So the second derivative never equals 0, but it's undefined at x equals 0, and this function is undefined at x equals 0. So if we create like a number line, put 0 here, so again the function's undefined, there's an asymptote here. So we'll check both sides of that discontinuity to see if the function is going to be concave up or concave down. So let's go ahead and test f double prime of negative 1. So if I plug that into the second derivative, so negative 1 to the third is negative 1, so this becomes negative. If I do f double prime of 1, that's going to be positive. So f double prime is positive for x is greater than 0, so that's where it's going to be concave up. So concave up, say from 0 to infinity. Okay. Find all points of inflection of the function. Okay. So points of inflection is when a function changes from concave up to concave down. So again, I'm essentially going to be using the concavity test to help me out with this. To an extent, sorry. So y prime would be equal to 27x squared plus 2. Y double prime is going to be equal to, what, like, is that 54x? And if I set that equal to 0, that's just going to be equal to 0 at x equals 0. So then if I plug 0 into the function, so y of 0, I get 8. So therefore, point of inflection that happens at 0, 8. And there you go. Okay, so that's the second page down. Again, I like to keep these videos short, so I'll stop it there and do the third page separately.